Really about seems SPDEs now, and we'll develop singular SPDEs in Hilbert spaces and some properties. Please welcome.
Thank you. So in some sense now we come back to business. This morning was like about nature of the noise, but now we are back to the solutions. And before I forget, later on, I will ask again this evening, in honor of our next speaker, we would like to go out to some pub together and maybe have dinner together and some beer. So if somebody wants to join, should let me know, because probably if it's a larger crowd, we have to make reservations because it's Friday night, right? Even in the Eel, it could be crowded.
In the Eagle, they don't do a reservation, actually.
Okay, so then we have to take our chances anyway. Okay,
yeah.
Good.
But you have to fix the time.
Yeah, maybe after the talk of one, we can ask people. Okay, sorry about this detour. All right, so now I'm going to talk about this invention of Feng Yu Wang, who is the next speaker. This is not the classical Harnack inequality as you know it from analysis. It's another type of parabolic Harnack inequality. And so Sasha Gregorian, also an expert on Harnack inequalities, now suggests to call it either Wang's Harnack inequality or to call it infinite dimension-free Harnack inequality. So, but I will explain exactly what it is. And this Harnack inequality, as was discovered by Wang, has an enormous number of very important properties. And just to put it in maybe your sort of mosaic of infinite dimension analysis and SPDE, it is, at least in this talk, it's very much based on Girsanov's theorem in the proof, though you don't see it somehow explicitly, because you do a kind of coupling argument, which I will not recall because it's classical, and there you can use Harnack, you can use Girsanov theorem, but it's not really necessary. But it sort of exploits the consequences of this much more than you have been done by just using Girsanov itself. So for instance, one consequence of this will be if you have this Harnack inequality for the transition probabilities of a solution of an SPDE, it follows automatically the SPDE has an invariant measure that every LP function, L1 plus epsilon function, with respect to the invariant measure, is mapped by the semigroup onto a continuous function. So not just the strong fella, so bounded functions are mapped into continuous function, but even L1 plus epsilon integrable functions are mapped into continuous function, which I know no proof whether this can be obtained directly from Girsanov without having recognized this dimension-independent Harnack inequality. This is just for motivation. It's joint work with Giuseppe D'Aprato and Feng Yu Wang, and has been published in JFA, I think late last year, so you can already find it there. Okay, so here's the framework. This is can be done, of course, more general, but just to fix a class of equations, and of course I use immediately the abstract formulation. Later on I will give you concrete examples. So there's such an equation on a Hilbert space, x takes values in a Hilbert space. A, as usual, is a generator of a C0 semigroup, and F is a nonlinear vector field on the Hilbert space, and here we have a cylindrical Wiener process. Sigma, so we just have additive noise. Sigma is just a map on the Hilbert space. Yeah? So H is the Hilbert space, we have the cylindrical Brownian motion, and A, for simplicity, we assume it's self-adjoint, and so it has this bounded upper and bounded from above. So omega is any number, so it could be a positive number. So it's quasi-dissipative case for people who know operator theory better, even better than myself. Okay, so there is now the following condition. So our sigma in front of the noise is a bounded linear operator, and just to go to the second property here, we also assume in most of the talk that it is invertible. So really we have true white noise there, and therefore concerning my remark on Girsanov, you really have the Girsanov theorem here if the F is, let's say, bounded or linear growth. Okay, and that is a condition, the usual condition on the semigroup generated by the linear part to have a mild solution, which is continuous, it's path continuous, so this is this part of the condition. This you only need up to 1, yeah? But this one refers to that we also have for the linear part of the equation an invariant measure. That's the standard condition. If that is 0, then this condition assures that there is an invariant measure for the equation. Okay, so that is, concerns the linear part and the diffusion coefficient, and now here's the nonlinear part. So I formulate this now quite complicatedly. What I really want in the equation is not this function f, that maybe you should think of a little f0 here. I will explain in a moment. And so this f0 you should put in the equation, which I'm now going to introduce. And this is the usual framework of monotone operators. So in general, they are multi-valued. So f is a multi-valued operator taking values in the subsets of H, defined on some subdomain, and it is monotone. So if you have u and v, if you have x and y in the domain, and u and v in the corresponding image sets, because it's multi-valued, it's a set, then you have the usual dissipativity condition. And it should be maximal, so if you take the identity map minus f, you take the range in this sense, so you take the union of x minus fx for all x in the domain, these are sets, remember this is set valued, then this should be the whole Hilbert space. And then I assume that my drift in my equation really is what is called the minimal section in this multi-valued thing. So I take that element in every set over x, which has the smallest distance to the origin. Okay, so you think of this multi-valued set, and you always take so in one dimension, you take always the lower point of this multi-valued operator. So here's the argument x, here's the whole set on top, and you take the lowest point. Yeah? That's the minimal section. And then for this minimal section, we have what is called the Yoshida approximation, the nonlinear Yoshida approximation. That is what we use. Yeah. Okay. So it is different from an approach to multi-valued equations where this is multi-valued, and then you define the solution in the usual sense in convex analysis or nonlinear analysis by first of all having a solution, and then you prove that exists some sections of this equation makes sense. I really want to go for the minimal section. Yeah, it's not the same, and so for later on I'll show you some examples where this is interesting. Okay, so we have a monotone nonlinearity. Okay, so now I would like not to solve this equation, this stochastic differential equation. I'm just interested in the transition probabilities of a possible solution, because under these general conditions, first of all, we don't know whether there is a solution for this f0. At least for this f0 is completely unclear. And so the point is now don't think about the solution of the SPDE. Maybe there is no solution, but maybe I can right away get information about the transition probabilities without even solving the equation. And you know how to do this. You consider the corresponding Kolmogorov operator. So that means the generator of the solution that maybe doesn't exist, but you can write down the generator. And the generator looks like this. There's 1/2. Here's the second order part coming from the Brownian motion. You see, here's the diffusion coefficient. And then there is a drift. I write it this way because A is not defined everywhere. And f0 of x, this is only defined for x in the domain of f. Yeah? So that is important. But here I can sort of cheat a little bit and write it in a weak form. So put this over to the derivative of my function phi. And the phi is now a function on the state space of my differential equation, so it's a function of the Hilbert space from H to R, and I look at the following function of this form. I take real and imaginary part of such functions, the sine and cosine functions, where H, so this is the inner product in H is in the domain of A. And then this makes sense, because if you take the Fresnel derivative of this, the H comes down and you can apply A. So the linear part you can always, by this trick, write it down, the operator for all x, but of course here you really have to make the compromise. It's there. And then you have to be careful what this means here. So if you write a trace class of this, you cannot write it down for CP2 functions, because the trace will almost never exist. But if you have a phi of this, which is finitely based, the trace always exists, of course. Yeah, because the trace is independent of the basis, and you just take this, you take a basis for a given phi, which just has this h as its first component normalized. So that's easy. Okay, so these are just we called the conditions. Now the first condition is this one, so quasi-dissipative and self-adjoint for the linear part. Then the usual conditions to make have an invariant measure for the linear part. We have sigma as usual, but this is the important condition, and f is maximal monotone in this sense. Okay, the additional assumption now we also need to exist an invariant measure for the whole equation, so not just for the linear part, so including the f. And later on I will give you an additional condition when this is always true. So there's not an abstract condition, but the analysis is best just to assume you have this invariant measure, because meanwhile there's so many different methods to construct invariant measures that we just want to assume existence, not a particular type of constructive measure. Okay, so we assume there exists a probability measure which sits on the domain of the nonlinear part, satisfies this integrability condition. So that means the drift is integrable, that's what we assume, and even norm square times this F0 is integrable. But in all cases, I mean, basically this is fulfilled. If you have an invariant measure, you can easily prove such properties. And it should be invariant for the equation, and of course, since we don't have a solution of the SDE yet, we just formulate the invariant measure as usual in terms of the generator. So L0 phi d mu is equal to 0. If you have an invariant measure for the equation, and this is always true, the converse is wrong in general. So this is a more general class of invariant measures, and they're called infinitesimal invariant measures. So an infinitesimal way to write down what an invariant measure is without knowing the semigroup even. Let it alone the solution of the SDE. Okay, so then under these four conditions, because F0 is merely measurable and sigma is not Hilbert-Schnitt, it is completely unknown whether SDE has a strong solution or even a weak solution is clear under these conditions. But as a consequence from our analysis, we will show, in fact, it has always a pathwise, unique, in the probabilistic sense, strong solution. But not from every starting point, but we can define a set of starting points for which we can start and have really a strong solution. So that is the outcome in the end after doing all this analysis, and Harnack inequality will play a crucial role in sort of this upshot at the end that nevertheless there exists a strong solution. For this F0 as a drift. So I'm not talking about the multi-valued thing, really the minimal section, which is the natural thing from a probabilistic point of view. Okay, now let's assume all these conditions. The only thing I drop in this theorem that I would like to recall is that sigma to the minus 1 is bounded. Yeah, so I do note sigma could be trace class, for instance, for this particular theorem. So assuming this condition, the part sigma minus 1 exists as a bounded operator, then for any mu satisfying this condition H4, so for any invariant measure with this condition, the operator can be modeled on L1 with respect to this space, and is there a dissipative operator, so in particular it's closable. Furthermore, its closure generates a C0 semigroup PT mu on L1. So that's the first result. It is in this old paper of Giuseppe and myself in PTRF. And this semigroup of operators on L1 now is conservative in this sense and positively preserving, so in particular Markov. And furthermore, the measure mu is really a true invariant measure for this operator semigroup. Just notation for the next slide. So these are the bounded measurable function on H. This is the continuous bounded function on H. And this is the operator norm, just to write things down more concisely. So that's the first theorem that is important for our work. So that means now we have the semigroup. Now we can talk about Harnack inequalities for the semigroup once we have this. The only problem with the semigroup, at least when you do rigorous analysis, is this semigroup is not clear for the moment whether it comes from a kernel, so whether it comes from measures. Yeah? It's just an operator semigroup. You do not know whether it has an integral kernel. In particular, we do not know whether it has a heat kernel at this point. Later on, it will turn out it has. And even this heat kernel has very, very nice properties, which all are implied by the Harnack inequality. Okay, so as we work with an invariant measure, and we have a semigroup, which depends on the invariant measure, this PT mu, pointwise statements about this semigroup can only be made on the support of this invariant measure. Because, I mean, we know from the work of Martin Heyer and Jonathan Mattingly how important it is if you have several invariant measures to study carefully the topological support of this measure. It might be many, this topological support might be completely disjoint. Anyway, so we can only make statements on the largest closed set of H with the complementary mu measure 0. So it's a topological support of the measure. Okay, so but now the theorem is under this condition. That's the first three, is a result also in this previous paper. No, sorry, this is, I'm sorry, I went a little bit too fast. But this is already, this is also in this previous paper in PTRF. So this one. Okay, so this is 1, 3. So assume these four conditions that before, then for any mu that is this invariant measure which satisfies the integrability condition I mentioned, there exists a semigroup of kernels now. These are no measures. For every x, this is a measure on H0. For every x in H0, it's a measure on H0. Such that if I apply this kernel to a function f, it is a version of this L1 semigroup. Okay? So where this is the usual definition of this PTF mu. And now here comes the most important thing. This semigroup of kernels has a property of mapping bounded measurable function into Lipschitz functions. So it's a smoothing. It's a kernel which is smoothing. This follows from our dissipativity conditions. So we have Lipschitz Strong-Feller property. And the Lipschitz constant is here, and you can see if t goes to 0, of course this blows up. But otherwise it's, and the sigma to the -1 now comes in. I assume the full condition H3, so sigma to the H2, so sigma to the -1 is bounded. So I have this type of property. You can construct such a semigroup, and this construction is really tough. So if you look at the paper, you have a better idea how to do it, but it's really a tough construction. And the other thing is we have pointwise continuity. So that if I fix x and t goes to 0, then this kernel converges to the Dirac measure. So for all functions f which are bounded in Lipschitz, we have this kind of property. And mu is in fact invariant for this semigroup. So without solving the SDE by these techniques, I get the transition functions pointwise, at least for x in the support, for starting points in the support of the invariant measure. Unfortunately, we cannot prove that any invariant measure has full support, so the whole Hilbert space. We have some techniques to prove this based on control theory, but so far we have not had the time to work them out in a better way that they apply here. But I think this is, in particular, sigma is invertible. You would expect that these measures all have full topological support. But we have no analytic technique to prove this so far. Okay, so we have now these semigroups, and now here's the main result of this talk, namely that this semigroup of kernels now, which is pointwise defined, there's no zero sets anymore to be excluded, pointwise defined on the support of the measure, satisfy what is called Wang's Harnack inequality or dimension-independent Harnack inequality. And I will explain this now, what it means. Okay, so take any Borel measurable function, bounded Borel measurable function, you apply the semigroup at point x. And you would like to compare this with the semigroup evaluated at y. Okay, so what has this to do with the Harnack inequality? Well, of course, PTF solves the parabolic equation it solves the heat equation for the operator L, right? So we are talking here about a space-time harmonic function. And parabolic Harnack inequality is exactly this. I mean, you compare a space-time harmonic function at two different points. Okay, you would like to have a constant independent of x and y, or if it's dependent, you would like to understand the dependence of x and y. So this is typically in analysis Harnack inequality. But now here it's formulated in a different way. It also gives a comparison between 2 points, but you pay a price. Namely, if you look here, I mean, you can put the p to the other side. So that means you compare the L1 norm of f at x with the LP norm of f at y, and p is strictly bigger than 1. So if you put this to the other side, forget about this term for a moment, then if x is equal to y, this is just Jensen's inequality. But if x is not equal to y, it's a highly non-trivial inequality. Okay, so you can compare your semigroup at 2 different points, which is fantastic, because if you have a property, for instance, of the semigroup that holds in y only almost everywhere with respect to the invariant measure mu, then you have it at least for one y. So you have it by this inequality for all y. So this Harnack inequality gives the possibility, if you have knowledge only almost everywhere, to get a pointwise knowledge as one application. There's many other applications, of course. Okay, and here's the exact estimate. So there is some function here. Typically in the exponents you have the distance function, x minus y here, comparing the 2 points. So that is the price you pay, and these constants are all positive. So that means it's e to some number which can be very, very large, and depending on omega. Yeah, so that depends if you have dissipativity probably is different, yeah, but otherwise, so this is what you have in general. Okay, so this is the comparison of the semigroup 1 point with respect to another, which is claimed here. And the proof I will explain later how we prove this. If I have enough time, I'll give you the idea of the proof. So one consequence which is completely general, by the way, this is wrong. It should be 1 plus epsilon. There's an epsilon missing. So pt mu of an L1 plus epsilon integrable function with respect to the invariant measure is mapped into a continuous function. And this is normally in infinite dimensions. Before I learned about Fengyu's work, I thought in infinite dimension you can never have any kind of smoothing in interesting cases of the semigroup, yeah, because in infinite dimensions, as Maliavar told us, we have no Sobolev embeddings, nothing. So the only thing we have is you look at an SDE, you prove the solution. You have a solution. You prove the solution depends on the initial condition, at least in expectation, in some continuous way, and then you get some smoothing properties of the semigroup if the conditions are very, very smooth. But now here you can see I assume almost nothing about the drift, just monotone, yeah, just dissipativity, but no smoothness at all. But nevertheless, the semigroup, the corresponding semigroup, always is L1 plus epsilon smoothing, not in the sense it makes it smooth, but at least continuous. Yeah? So for me, also, I think it was well known that for bounded measurable functions, something continuous comes up. But this was new in this paper when we realized for L1 plus epsilon, this is also true. And this has a lot of consequences. Just one consequence, if you have Harnack inequality in this sense, and the corresponding operator L is symmetric, which is not true in this case, so with a symmetric semigroup, it follows immediately that, first of all, the semigroup has a density, a heat kernel, and the heat kernel is separately continuous in X and in Y. I have no other idea how to prove this by other means in this general situation. But this is only if L is symmetric. We have no proof for that if it's not symmetric. Okay, so that is one consequence. Here's another consequence. It follows automatically from Harnack that the invariant measure is unique. Can be only one invariant measure. And this was worked out very nicely in the thesis of Wei Liu, one of our joint students. It was not quite applicable in our case because we're in a more general situation, but basically we benefited from his work. Okay, so now because now the measure mu is unique, we proved this, we can drop the mu, right? So there's really no other mu inside, so we can just call the semigroup ptx dy. And here's another thing, that's a general consequence that I think Feng Yu realized several years ago already. If you have Harnack inequality, then you always, because we have strong Feller, in particular strong Feller, if you have strong Feller, you always have a heat kernel. Right? It's a very simple proof, one line. So you have a heat kernel, but you have this very nice estimate. Namely, in particular, the heat kernel as a function of y, so where you integrate, so if you apply the kernel, you integrate in this variable, then in this variable, the density is not just L1 as a normal probability density, but it is even LP with respect to the invariant measure. And we have this estimate. Okay? Of course, it depends what your measure is, because you do not know, is this integrable, is this not integrable? Sorry, this is all positive, so this is always fine. Sorry. So that's always fine. So it's always in LP. Another property, and I'll just mix this up, is if the measure is very concentrated. So in that sense, that it integrates the exponential function for a sufficiently large lambda in terms of my data of my equation, then something falls, which is also not so often the case in infinite dimension, namely PT is hyperbounded. So PT maps L2 into L4, at least for large enough t. Okay? So of course this has, you know about hypercontractivity, this is hyperbounded, it is not less than 1. So we have some constant on the right-hand side. Of course, this hyperboundedness is not so surprising because we know, for instance, for Gaussian measures, we have hypercontractivity. So this kind of smoothing property of the semigroup, so being smoothing in the sense it maps L2 function into L4 function, not smoothing, is improving integrability. This is, of course, well known from the Gaussian case. So it's maybe not so surprising that after perturbing with the dissipative drift, which is maximal monotone, this is sort of preserved. But we have a much stronger result in the next theorem. So it's in the second part of this theorem. So let me first start with the first part. So in the case, let's say sigma is identity for simplicity, otherwise the sigma norm to the -1 pops up everywhere, and I want to avoid that. So now suppose that our nonlinear part of the drift, the minimal section, is, let's say, more dissipative in the following sense. So we have this kind of inequality up to a constant that is minus this function phi, and this function phi becomes big when the difference between x and phi becomes big. So that's the condition we need. There's lots of examples for this, of course. So it is some kind of a stronger dissipativity assumption, and the precise properties of this phi is up there. So phi is positive, strictly increasing, and it increases to infinity faster than linear. In this sense, and also faster than linear, that this integral should make sense. Yeah? So these two conditions. It's something that goes to infinity sufficiently fast for large distances of x and y. And under this, we even have the semigroup is ultra-bounded, which is something almost unheard of in infinite dimensions before. I don't know any result without these techniques to get this hyperbounded. So it maps L2 in L infinity. So this is I think it was written even in some papers that this can only be expected in finite dimensions. But by these techniques, it is also provable in infinite dimensions. And we have the precise upper bound. So it's ultra bound. It's not ultra conductive because this is not 1. Yeah? But it's ultra bounded, and we have the precise bound here. Okay? So that is I think it's, at least for me, it was very surprising. I will not give you the proof of this theorem. So the first thing is I already mentioned, I skipped this now, namely that for a set of full measure, we have a strong solution, strong in the probabilistic sense, of our SDE. So this comes out. The price we pay that we can only do it in a set of full measure of starting point, not for every starting point. So this, at the moment, we have no techniques to specify more precisely this set. There just exists such a set. But then we have that the solution is really a functional of the Brownian motion you stick inside. Yeah? So it's not only probabilistic weak, it's really probabilistic strong solution. And there are some techniques come in. So in particular, what we have to prove pathwise uniqueness because we use Yamada Watanabe. So the technique is first, using our transition function, we construct a Markov process in the sense of Kolmogorov with continuous, so using Kolmogorov's technique, and then prove this Markov process has continuous sample paths, and it solves the equation in the sense of the martingale problem. So we have a weak solution. And then we prove we have pathwise uniqueness. And this follows from the dissipativity, apart from the fact that we work with mild solutions. Yeah? The A, we have to work with mild solutions. A is unbounded. And then one has to work a little to prove pathwise uniqueness. Yeah? So I know in almost all books we know, when they work in such a situation, A plus F dissipative, the proof they do is heuristically. They just assume they have an Ito formula and do the proof. Because this is wrong. I mean, formula is wrong. Yeah? So you have to work a little harder how to prove uniqueness in these cases, even when you have such a linear path. So you have to work with the stochastic convolution. Anyway, so this was done in a very simple case here. So later on with Carlo Marinelli, we have a general paper about that. But here it was just a simple case. We could prove pathwise uniqueness and then apply Yamada Watanabe to prove we have a probabilistically strong solution. That is part I. But as I said, I cannot give you the details. We use beautiful paper of Martin Ondrejat where he proves the Yamada Watanabe in the case where you have a mild solution, not a solution, the usual solution of a stochastic differential equation. There's quite some work to be done in the case of cylindrical Wiener processes to prove also that you have a Yamada Watanabe principle there. Okay, and we also use a heavily result of Wilhelm Stannard for this 99 paper in Analysis Scola Normale. Okay, but this I will not give you the proof of this. I rather give you the proof of the Harnack inequality, which is really the heart of the matter. So I'm going to prove this inequality now, at least explain how to prove it. And then all these things follow. Also for this result, for the ultraboundedness, we use Harnack inequality to get an estimate on the right-hand side. Yeah? So it's all related to this inequality. Okay, so now how do we do this? We first of all take our function f, and we can look at the corresponding, what is called Yoshida approximation, very well known in convex analysis. So what you do is you, first of all, you look at the resolvent of f, so you take the identity map minus alpha times f to the minus 1. By dissipativity, you realize immediately this is a single-valued function, no longer multi-valued, f is multi-valued. And then this map is this map is composed, as you can see here. You take minus the identity again, 1 over alpha, and then the main point is f alpha is a single-valued Lipschitz continuous function. Of course, the Lipschitz constant explodes when alpha goes to 0, because when alpha goes to 0, you converge exactly to the minimal section. That is very well known. So you can find it in this beautiful new book of Virel Babu in 2010, Springer lecture notes. So all these things are now written up, I think, in perfect form, most modern form. You will find all this, so that this increases, so this converges in the domain of the function. F0 is the same domain as the multi-valued function, as I said before. And it is, in fact, it is even increasing. So this in norm increases to this F0. So in particular, it's smaller. This is very important because you think we have an invariant measure, so this helps to apply dominated convergence theorems a lot later on. Anyway, so we have a Lipschitz function, which is again monotone. That is another thing I forgot. No, it's dissipative. It's written here, but the Lipschitz constant, as I said, explodes. Unfortunately, we need another approximation. It makes this thing a little bit more complicated, but It's life is sometimes not easy. So f alpha is not differentiable, it's just Lipschitz, so we make it differentiable using a standard regularization, for instance, from the book of the Prato-Zaczyk. So we just do, in a sense, a convolution with a Gaussian measure to make it smooth. It's not so important, I just want to be precise here. And B is just self-adjoint negative definite operator, trace class, so this measure makes sense. And then if we take this, now if beta, now this, the parameter beta, goes to 0, then this converges to f alpha. Okay? So we have this convergence as beta goes to 0. The good thing now, f alpha b is still dissipative, it's easy to check. Now it's even C infinity, and with a bounded derivative, so f alpha beta is still Lipschitz. And we have a growth, a linear growth, which is independent of beta. Depends on alpha, but not on beta. This is also important, but nevertheless, it's just to tell you the truth. Okay, so now we have the following result, and this is again from this paper in PTRF 2002. You look at the approximating equations, where you replace f by these smoother drifts. You look at the corresponding solutions. You look at the corresponding semigroup. This is point-wise defined. You can start at every point. Everything is nice. And then what I proved with Giuseppe, that we have a convergence if alpha goes to 0, beta goes to 0, at least for some subsequence, so that then this semigroup converge to the semigroup that I talked about before, this strongly Lipschitz-Feller version of the semigroup from the previous theorem. So now we can, of course, we can drop the mu if we can prove Harnack, yeah? But now I still put the mu, we have not proved Harnack yet. Okay, so that means now look at this conversion, it's extremely weak. Yeah? So it says that fix f, bounded measurable function, apply to x in a set of measure 1, which is a union of compacts, so in fact, is a k sigma set, it's not so important. And then you can only prove basically for almost all fixed x here, because it's only measure 1, that this converges in T in this L2 space in T. These are now, as a function of T, are just in this space, and we can only prove it converges weakly in this L2 space. So it's a very, very weak way to prove. And it's, I asked many, many experts, they say, okay, if you have this, you go to the limit, you should be able, that the process x alpha beta converges to the solution of your limiting equation, then you have your solution, life becomes easier, but we were not able to prove this. Yeah? So we cannot prove tightness even under these general conditions. So we can only prove convergence of finite dimensional distribution in a very, very weak sense, because we have no smoothness on this x0 at all, no continuity, nothing. And then, as you know, if you have no continuity to go to the limit, you can use the dissipativity, but then you get into the problem at the end in the limit that you don't get the minimal section necessarily for your solution. So there's another section that you have to choose. So these techniques are not suitable. So we had to invent a new technique, which we did in this paper. So now it is easy to see that these semigroups with the very, very nice drifts, they satisfy Harnack. So now the name of the game is to prove then the limiting thing also satisfies Harnack. That's all. Okay? So first of all, now let me explain why these define really satisfy Harnack. So that's a sort of the standard part of the proof, but nevertheless, since probably Feng Yu will also appeal to Harnack more, I should give you some confidence why for nice drifts we have this Harnack inequality. And then you go to the limit. So let us assume we are in such a situation, and we only need that this is Lipschitz. We don't need this smoothness. This was only necessary for other reasons. Okay, so now let us assume f0 is Lipschitz. And we don't need the invariant measure here, so just like this. Okay, so then we know the equation for Lipschitz nonlinearities. I mean, this is sort of the trivial case, so very, not trivial, very well known, I should say. So you look at the corresponding semigroup, and I would like to prove this semigroup is now, satisfies the Harnack inequality. And you proceed by usual Galerkin approximation. You take an eigenbasis of my self-adjoint operator, so we assume here that it has discrete spectrum. So we take an eigenbasis, and then we just do a Galerkin along these eigenbases. So that means we take this, and then the usual thing, and this. So everybody knows this. Then we have these finite dimensional equations. The only slight twist is that this will not converge to a Hilbert-Schmidt operator. So you have to be a bit careful. So if it converges to a Hilbert-Schmidt, then everybody in this room can do this, of course, in 5 minutes, what I'm explaining you. If it's not, you have to shift away the stochastic convolution in a proper way to control the convergence. It's not difficult, but I'm just mentioning this. If you want to precise, you have to be a little bit careful there. Okay, so then we are in finite dimensions. So in finite dimension, Harnack inequality can be very easily proved by a coupling argument. I will not go into this, I'll use Kirsanov theorem, but so this is sort of a well-known result since maybe more than 10 years, but thing you write that for the Lipschitz case in finite dimension you have this Harnack inequality. Okay, so now the thing is then you prove that the solution converge along the Galerkin, so the semi-loops converge at least in a set which is the union of the Hm is just the space spanned by the first m eigenvector, so at least in this union which is dense as one can see, so the closure of this is dense in the space. So you can, for sufficiently many points, you have this convergence. Okay, and yet for the approximating ones, the standard method, the standard coupling method, give you Harnack, and then of course you have Harnack for the limit, because here you can go to the limit, right? So even if you only know this for CBH function, you first put this f to be CBH, right? And then you can take limit here, you take limit here, and this doesn't depend on n. Done. Easy. And you can do it for all xy in this union, yeah, because they increase these HMs. Yeah? And that's enough, because it's a dense set, and we already know the limit then, I mean, can be extended to the whole, for all x and y in all of h. Okay, so then you have this, so that means in the case f0 is Lipschitz, we have that Harnack inequality hi holds. So the first part is the most work to prove this convergence, finite dimensional, the usual coupling argument. Maybe Feng Yu will tell us more about, I don't know, but otherwise, of course, we are open for questions. Okay, so now let us see whether we can actually take the limit. So I'm going to use this convergence now. So I know Harnack for these guys, okay, and so I would like to prove Harnack for these guys. One thing I forgot to mention, if you can prove Harnack for these guys for Lipschitz function, it's enough. Then by approximation it works for a bounded function. It's very simple. Yeah? So you can always have, let's say, a bounded Lipschitz function that you like and prove Harnack for those functions. Okay, so now let us go to the how can you prove it's a limit? So we take now a bounded Lipschitz function, and here we want to prove that this is less or equal to this times this constant. I've just taken the 1 over the up to the p to the other side. Yeah? So we would like to prove this, and then it's this constant e to the distance, essentially. And so how is the proof? Remember, we have this convergence of these guys to these guys only in T, in weakly in L2. Yeah? So the trick is easy. You just write this thing as a combination, so of PS mu F, so simply using this kind of smoothing argument. And what we use here very heavily is that we have right continuity in S. And this was one of our results from the previous paper in PTRF 2002. Otherwise, this cannot be done. So you really have to use that for every bounded Lipschitz F. This is continuous in S. Otherwise, this does not converge to that. Yeah? Okay, now we are done. Now we can use that this converges weakly in S here, right? So we just call this function here, which we write this as integral from 0 to t plus 1. Inserting this indicator function, and then you put it there, and then you can use weak convergence in S because this is in L2. Okay, so this weakly converges, this is a weak limit of these guys. First taking M and then taking N. So we are here. Now I use Harnack. Okay, so this is less than the P norm of this 1 over P. Use Jensen to take the P out, so I end up here. Okay, so you really see, now we can do the same thing again. We first of all take this inside, this is in L2, we have weak convergence in L2, this does not depend on, this does depend boundedly on S because we integrate over an interval, so we can take the limits back in, and then we just take this out, and so this P goes out, because I have to take 1 over P, that's it. So we have then, for all x and y in a dense set, this was only true for all x and y fixed in a dense set, we have this, but then we can, because this is a dense set in the Hilbert space, we can just go to the limit here in x and y, and so we are done, because we know beforehand if f is Lipschitz, this is continuous in x. Yeah? So we can take, if we have this for a dense set of x and y, we have it for all x and y in the Hilbert space, or in our, as I said, in the support of our invariant measure. So then we are done. So we have it for Lipschitz functions, then for all x and y, and then we go to all bounded function by simple approximation. Okay, so we have our Harnack inequality. So we have proved our first main result. Let us go back. This one. Yeah, in this very, very singular case. Okay, so then I promised you also the proof of this corollary, where here's the mistake, it should be 1 plus epsilon. Sorry. Okay, so now let's look how to prove this.
Can you remind what is H0?
H0 is the support of the invariant measure. Okay, so it's a subset of H. Yeah, maybe I should write it here. So we have H, and we have a smaller space H0, which is maybe not linear, and this is defined to be the topological support of the invariant measure. Once we have Harnack, we know it's the unique invariant measure, so we work on the right space. You know? We have not lost any information. Okay, so now let us prove this continuity. So now let's just, for abbreviation, put pt mu, I just call equal to p. And now the idea is the following. Let me first explain the idea. We are going to prove this inequality. So we take an f in LP, p is strictly bigger than 1, so p is 1 plus epsilon here. And we know that we can always approximate our f in such an LP space by bounded function, just doing this. We can take f to be positive, because otherwise we write it as positive minus negative part. So take it positive and take it infimum. So now this is bounded. So we already know by general result, which I have not proved here, but this is what I'm going to use, that for bounded functions, for these approximants, my pt mu, so p, apply to fn is continuous and bounded. This we already know. Now I would like to prove why this goes over to L1 plus epsilon functions. Okay, so what we prove is, for the approximations, I prove this uniform bound, like this uniform bound. And here I take a particular y for which this is a Cauchy sequence, for the corresponding measure, you know, with y fixed. Suppose I can find such a y, then this becomes small for n and m large, and this becomes small in a ball around y, and this is the ball. So the ball is given basically here by this distance, plus cosmetics here. Okay, so I take this y, for which I know this converges, I look at the ball around this y with respect to this metric, and I prove uniform convergence of my functions on this ball. Okay, if I can find such a y, I'm done, because I know these are all continuous. Yeah, because they're bounded, and I already know Strong-Feller. So I have proved the uniform Cauchy sequence on this ball. So that means the limit, namely pf, because fn converges under p, of course, to pf of x, the limit must be continuous on this ball, and this is true for any ball, so we have continuity. So that's the idea. But now the question is, how do I get this inequality? So that is the main point. Well, here I simply use Harnack. I take absolute value inside, okay? So first I have p so p, first I have p outside, like this. So I take absolute value inside, not the p. Okay, now I take the p inside by Harnack, and I can replace by y. That's exactly Harnack. Okay? So I only need one y for which this converges. And this is e to the pn, where n was originally this distance between x and y. Okay, but now I just take the soup of the distances here. So this n is just the soup of the distances. Well, it's defined, yeah, here. Yeah, it's just the radius of this ball. So I can estimate what is up here simply by n. This is fixed. Okay, so I only have to find one y for which this converges in LP with respect to the measure given by p sub y. And that is very simple, you see. Because we know this p is a bounded semigroup in LP, because it's a Markov semigroup. It's not only in L1 a bounded semigroup, it's in the bounded kernel, I mean. In L1 it's also in any LP, because it's sub-Markov, it's simply Jensen's inequality. So we know that this is true. It converges in L1, or even LP if you like. Yeah, so this converges. So that converges almost everywhere. First in L1 and then take a subsequent that converges everywhere, almost everywhere. So in particular there exists one point y where it converges, and this one I take. So that's the power of Harnack inequality. For just one existence of one point with a good property, you have it for all points. And then you get this. So I hope I've given you some idea of how important this Harnack inequality is. And finally, I would like to talk about my condition that such an invariant measure exists. So we just assume this invariant measure. So far, everything is conditioned that we can find this invariant measure. And now I would like to give you a condition under which this, of course on the coefficients, so that this invariant measure exists. So the first one is the following. We just assume that we have dissipativity, so not just less or equal to 0, but some dissipativity of my nonlinear part. But please note that the dissipativity takes into account the dissipativity we have from the linear part. So if the linear part is the Laplacian, let's say on some bounded interval, let's say one-dimensionally, then of course this omega is a negative number, could be quite big negative number. So then I can really allow you a positive eta. Yeah? So this depends, it takes into account the dissipativity which is given to us as a present from the linear. Okay, so it doesn't have to be strictly dissipative, this f. Okay, so that's the first thing. And then we can construct an invariant measure as follows. Take the Yoshida approximations. Then we are in the Lipschitz case. The Yoshida approximation have the same type of monotonicity, so we can use for Lipschitz functions which are dissipative the classical result that the corresponding process has an invariant measure. Take those invariant measures mu alpha. Yeah? And then, for instance, from Da Prato, we know we have this uniform bound on these guys with respect to, in this situation, with respect, so that means the mth strong moments are uniformly bounded for these approximating measures of the Hilbert space. So this is, for the Lipschitz case, all is very well worked out, for instance, in this book of Giuseppe. So then look at the invariant measure of my linear part of the equation, which is given by the Gaussian measure with this covariance operator, as everybody knows in this audience. And then we do the following. We look at the corresponding Sobolev space with respect to the Gaussian measure. So this is, as you might call it, the Malyavin Sobolev space of order 1, 2. Yeah? Okay, but it's not really Malyavin because this Q is not is really is a nuclear trace class operator, and such the Sobolev spaces for such Gaussian measures have much better properties. In particular, so this is just the Sobolev norm. Okay, and of course these are the exponential function, but you can take the completion and then you get the full Sobolev space with respect to that Gaussian measure. And what is important here, this was proved in this old paper, that in the case where this is trace class, this embedding is compact. This is not true in the Malyavin calculus, yeah? But in this case it's true because we work with a different Gaussian measure here, not with the standard Gaussian measure. Okay, and then we have the following theorem. So if we have our three conditions, H4 was the existence of invariant measure, this we drop, we want to prove that it holds. We have this dissipativity condition, and then we need this abstract condition, and I will explain why. So we need a function which is bigger than the drift, okay? And it also must be defined where the drift is finite. And this function is uniformly square integrable with respect to the approximating measures. I will give you a concrete example of such a G in a moment. Yeah? So this is what we need. And then we can prove the following, that mu alpha is tight. You can imagine from this we get that tightness. So it's tight, and any limit point satisfies our condition, so it is an infinitesimal invariant measure for our Kolmogorov operator for the limiting equation, and we have the integrability properties stated in H4. Okay, so hence by our corollary, we have Harnack in this situation because we have all the other conditions then. We have Harnack, this measure is then automatically unique, and then by lower semi-continuity, it has this very nice property. And now is the surprising thing for me. In fact, this measure we get has a density with respect to the Gaussian. Though the F is not bounded, not Lipschitz, is quite singular, nevertheless we keep the property that the invariant measure is absolutely continuous with respect to the Gaussian, and the square root of rho is in W1. I'm sorry, this is a misprint, it should be NQ. So it's really in the Gaussian Sobolev space of order 1. And in the next 5 minutes I would like to explain the technique how to prove this. So this is sort of the leftovers of Sobolev embedding in infinite dimensions, what we use here. Some things are still true, and this is what we use. And one is this one, this compactness of the embedding. Yeah? So this is sort of what is left from usual embedding theorems, which you have an abundance of when you work in finite dimensions. And this has to be used here. And I will try to explain what it is. Okay, so first of all, we know for the approximating measures, they are all absolutely continuous. This we did in a very old work in applied mathematics and optimization many years ago with Vladimir Bogachev. And we have that the square roots are in the Sobolev space, so as we would like to have is also true for the limiting measure. And we have this uniform bound. That is really the main observation. So that means the Sobolev norm of the square root is bounded by the drifts in the equation. This is in this paper. That's the most important thing. But now remember, these guys are smaller than G. So first of all, smaller than F0 because they are approximations, Yoshida approximations. But this F0 in our condition is smaller than G. And we have this uniform bound on the G. So we have a uniform bound on the F0s. So we have a uniform bound on the F alpha. So the right-hand side is uniformly bounded. So we have uniformly bounded Sobolev norms. Okay? But if we have uniformly bounded Sobolev norms, this means we have convergence in L2 because this Sobolev space is compactly embedded into L2. So we know these guys converge in L2 by this compact embedding. Okay? And if this converges in L2, of course, then without the square root converge in L1, so we have a limiting object, namely this measure, rho times NQ. Now, since G is lower semi-continuous, we get automatically for the limiting measure this estimate that we need, that I claimed. You remember I claimed in the last line, sorry, this, no, where's the zero? Here's the zero. So I claimed this sim. So now we have this for G square. The G square is bigger than F0, right? So this follows, we even have this with G square. This follows simply by lower semi-continuity, because the G is by definition lower semi-continuous. So we have everything. The only thing we have to prove that the mu really is an infinitesimally invariant measure for the limiting Kolmogorov operator. So there's work to be done. Yeah? But this I skip here, because these techniques we developed for many years and they just apply here. So it's nothing new here with respect to much earlier work. Okay, so we have an invariant measure in this sense. Now, this was a general technique to prove that an invariant measure exists with all the properties we need. By the way, what I forgot is that the limiting measure is really invariant, infinitesimally invariant measure for that Kolmogorov operator, though the coefficients are not continuous, uses the fact that the convergency of mu alpha to mu is not just weak convergence, it's tau convergence. So it converges when you integrate against any bounded measurable function. So continuity is completely out once you have this uniform integrability result that we have inside here. Yeah? So therefore you can handle non-continuous coefficients, otherwise there's no chance. We have a much stronger convergence than weak convergence of the approximating invariant measures. Okay, so here's an easy example. So you take HL2 over the interval 0, 1. You take Lebesgue measure with Laplacian with Dirichlet boundary conditions, and you take any decreasing function, let's say polynomial bounded. So now to put it in our picture, I mean, this is a general technique I learned from Biorel-Barbou. You make, first of all, this function, which is so it's a decreasing function. So first what you do with this function, you make it multi-valued, and because it's not continuous, first of all not continuous, you make it somehow into a multi-valued continuous function. So you look at the jumps, and you know it's a decreasing function, it's only countably many jumps, and you just fill in the gaps. So then it's still not continuous, but the gaps where it jumps, you fill in by a multi-valued function. So in that sense, you have now sort of continuous function. Okay? All right, so then if you compose this function with x, because this f will be this little f will be my big F, just the corresponding Niemitzsky operator. So you look at the corresponding now multi-valued map on my Hilbert space, which is L2, you do this construction, and then you take the minimal section of this function. This corresponds, of course, here to the minimal section of this f bar, basically. So you take always the lower end of the jumps. Okay? So then we are in business. So then I can solve this equation with this f0, with the Laplacian, here just cylindrical Brownian motion on L2, and I think all is satisfied. We have an invariant measure, all the results apply, apart, of course, from the result that we have ultraboundedness, because remember, we need very strong dissipativity of f0. But of course, this can be built into two such functions. You can easily find functions to have this very strong dissipativity that I mentioned to have ultraboundedness. And now what is the function g? Because I claim there exists an invariant measure. I have to tell you what is g. But this we already did in our old paper. G, you just take the LP norms, the x is in L2 originally, and you take g to be the LP norm, so p equal to 2m. If it is finite, otherwise you put g to infinity. Then this function g is exactly the function that satisfies all the properties in this particular case. So that is one example. You can do other examples, but the time is almost up. I just want to mention one thing at the end, which is, I think, necessary that I mention this here. So when we submitted this paper, the first referee rejected this paper, saying it is just pulling in Harnack inequalities from Lipschitz case to non-Lipschitz case, nothing else. So he ignored 2/3 of the paper. He was just talking about the first third of the paper. Second remark was, there is no examples in the paper, no applications, but I can think sort of what kind of examples they mean. So he has also not read the last third of the paper, only the first third. And I really would like, of course afterwards the paper was accepted, but this I think is absolutely unacceptable, and I think it should be made public, such a behavior. I would call it scientific misconduct. If somebody claims to have read the whole paper, comments only in the first third, and claims even the last third is not in the paper. So I think this spoils the referee system, and I think it should be made known to everybody. So I think such bad examples should be really taken out. Such referees should not referee papers for that journal again. But okay, apart from this a bit offensive remark, I hope you enjoyed the talk. Thank you very much.
Thank you very much. So there's time for questions and comments.
Michael?
Yep.
Yes.
You're assuming that the sigma invariable, will that limit to one-dimensional problem?
You mean about the invariant measure?
No, I mean,
Sorry.
in general, you have a, say, parabolic equation,
Yes.
and with the differential white noise, right?
Yes. This is, of course, a very good remark, because you see here, I can take the white noise because I'm in one dimension. Yeah? So I have the Laplacian, and then in one dimension I can take the white noise because the Laplacian is a very good operator with the trace class resolvent and so on. If you go to higher dimensions, what you have to do is you have to color the noise in a very particular way, as it usually done, for instance, in the book of Zraptik and Taprato. You have to put Laplace to the minus epsilon in front of the noise, where epsilon depends on dimension. And in such a situation, we still have this result. Yeah? But you really have to color it. That's a very important thing. The absolute continuity of the invariant measure is still okay. Yeah? Because this compactness embedding is still okay, because this is dimension independent. It's only about the application of Giersanov, yeah, to prove Harnack inequality. You have to be careful, because you get a different metric on the right-hand side. No longer the L2 metric, but you get a metric which is a little bit smoothed by this Laplace to the minus 1. So therefore, we need some modification to the proof to really do this case. It's complicated, so therefore I haven't done that. And in fact, we are still planning to write this up in detail. So just bear in mind. But you're completely right.
More questions? I have therefore two questions. One, in this example 5.2, so suppose everything is fine, how far you can change your Laplacian into fractional power of Laplacian?
Of course, if once you take a power which is smaller than 1, yeah, then of course you get into trouble, because it's no longer such nice. Does no longer have such nice trace class properties for the semigroup. So that means the usual condition to write down the stochastic convolution may be not fulfilled. So that's
Yeah, but suppose we have still good power.
So if the alpha is not too small, yeah, compared to, so that it still works in one dimension, this is independent of the Laplace. But you have to be careful. You need always to check this trace class condition e to the TA. The Schmidt norm of that must be integral from 0 to infinity. That's always the thing you have to check.
Second question, what about f non-decreasing?
I mean, this is the main point. We use dissipativity all the time. Of course, if it is only, you can always make it more general by saying it's maybe it's non-decreasing, but if I add some linear, it becomes decreasing. So that's the usual quasi-dissipativity. You can do this as long as you have sufficient big small linear operator. This omega must, of course, be coordinated with this. Otherwise, it doesn't work.
When in the deterministic case, you can't have blow up.
Otherwise, it can blow up. Exactly.
Sure.
Yeah.
So
But you can take sort of the dissipativity from the linear part and trade it on the non-linear.
really, what preparation question to the next question is, what if you don't have monotone systems? Like, for example, 2D Navier-Stokes, where you have invariant measure with all your bounds. Is it possible to have it and you have in white noise?
Okay, so this is a tough question.
Simpler
I cannot say right away we can or we cannot.
Simple equation, Burger's equation.
So, yeah, even Burger's is the same. So, in fact, now I mean, probably Istvan knows this very well. I mean, this monotone approach, so variational approach to stochastic PDE can be modified by going to a kind of localized version of the dissipativity condition to also cover the 2D Navier-Stokes. For instance, we haven't never seen it written up, so we have recently submitted a paper, Vail, you and myself, to pin this down. So it really completely fits into this monotone framework with a little bit changing the dissipativity condition in a very surprisingly simple way, by the way. So now we have hope, because there is general results. I didn't mention that, for instance, by Feng Yu, he was able to prove Harnack inequality for the stochastic porous media equation, at least if the underlying domain is one dimensional. And where you has generalized this a lot, and it is very important to have this nice variational approach of Istvan, Nikolov, and Boris-Rozovsky. It's sort of tailored to exactly check the coupling method directly in infinite dimensions. And so my hope is now that for Navier-Stokes, by this localized dissipativity condition, we have some chance also to prove similar things for Navier-Stokes. But we have to have a lot of nodes. And so far, the white noise case is difficult for 2D Navier-Stokes. If you color it a little bit, it might work that we have Harnack. But at the moment, I cannot give any guess, because it's very, very delicate. I mean, how to choose this epsilon in front of it. If you take minus Stokes Laplacian to the minus epsilon, so this epsilon is very delicate. Maybe we cannot choose it big enough for our purposes. So this is to be checked in the future. Sorry.
Yes, Mr.
That question here in this example that sigma is separated away of 0 in this example.
Definitely, yes.
But then you don't need a monotonicity condition because then any measurable will give a strong solution.
Right, this is your result, yes,
Yeah.
sure.
And
That's for sure.
only the explosion should
Absolutely
be
right.
prevented.
You see,
and
this
that's it.
completely correct. So if you just, this example is not for the existence. So for the existence, I mean, the
And
general...
uniqueness as well.
I know, also uniqueness. Uniqueness is no problem, it's the existence is more problem.
Yes, uniqueness is not problem in your case
Right.
when you assume monotonicity.
Exactly, exactly.
But what I am saying is that neither so the uniqueness and existence hold if sigma is separated away,
Right.
0, no monotonicity.
That's
is
correct. That's
needed.
by your result with Pardoux. Yeah, I know. I forgot to mention this. So
you were
this
aware of
example is not for existence and uniqueness. This can be done also by other method. It is just in order to show we have in this case this uniqueness of invariant measure. We have also this follows, by the way, probably also for new method, and in particular we have Harnack. Yeah, so that is really the new thing about existence and uniqueness. We still claim in the general case there is no result. In this case, there is a result, definitely. We studied this result already in the old paper with D'Aprato in 2002, and we mentioned there that there is another way of proving this.
So I don't see any more questions, so let us thank Michael for